Why don't we go ahead and get started? So just a quick overview of the agenda for today's talk. Just going to start off with an overview of what do we mean by decorative PVD coatings. I am going to give a brief tutorial of how the coatings are made, since there's many of you that are beginners and are new to PVD. I thought it'd be good to get everybody level set. And then I'll go into some more detail about the types of decorative PVD coatings, the different materials that are used and how they're made. And then I'm going to finish up with a little discussion about color assessment. It's a pretty important topic when you're discussing decorative coatings, being able to assess color, judge color visually and with instrumentation. So I'm going to talk a little bit about some of the best practices and some advice in that area. And then, of course, as questions come up, please feel free to add them to the list, and we'll cover as many as we can at the end of the talk. Okay, so getting into our overview. So the first thing I like to just reinforce is that when we're talking about decorative PVD coatings, the important part is the durable. We often call them durable decorative PVD because for most applications where these types of coatings are appropriate, durability is an important aspect of why they're chosen. Whether it's for wear resistance, needing a hard surface, or if it's just for chemical or corrosion resistance. But there's got to be some kind of a driver just beyond looking great. It's got to also perform. And then when we look into the types of coatings, I like to categorize them in two different ways, either as what I'd call natural finishes, where we're really trying to represent natural alloys, golds, coppers, bronzes, where they have these distinct colors, where we're using other materials in order to enhance the properties of a coating, yet maintain the look of another kind of material. And then the other kind are what I like to call artificial finishes. And these are ones that may not be quite readily available in nature, things like black, dark gray graphites, blues, rainbow colors, etc. So these are made in a little different ways, and we're going to go into that a little bit later, but just to give you a glimpse of how we like to think about these. An overview of the markets that we generally work in and that you find these coatings. Over here on the left side, some of the original areas in which they were introduced, especially the jewelry. This is where they were really first introduced back in the 80s. Watches, rings, and such were really where PVD coatings found their first use as decorative applications. Then quickly moved into door hardware and plumbing fixtures back in the 90s. Of course, everybody remembers polished brass being quite a popular finish back then. Zirconium nitride coatings, which we'll talk about, really became a mainstay and a way to provide lifetime finishes in those industries. Then moving on, sporting goods, firearms, we're really seeing a lot of new work in the firearms, starting to embrace decorative PVD coatings. Moving on to consumer electronics, it's very likely that those smartphones you have in your pocket have some kind of a PVD decorative coating on it. And then, of course, automotive, both interior and exterior. This isn't a comprehensive list, but these are where you're going to find these coatings most often. Okay, switching gears, how these coatings are made. So the majority of these are made by what we call physical vapor deposition, or PVD for short. This is a method by which we start with a solid material, which we often call a target, which is represented by this disc on the left side. So what we're trying to do is take that solid, remove material in the form of atoms or ions or molecules from that source by use of some kind of an energy, whether it's a plasma energy or a thermal energy, whereby you transport that material that has been converted into a vapor, hence the physical vapor deposition. You're in some kind of a controlled medium, usually a vacuum chamber backfilled with some kind of gas to control the types of properties you're looking for. That material transports from your target through that medium and lands and condenses and reacts on the surface of the substrate. So this is the part that you're looking to apply the coating to. We call them substrates, just for nomenclature. But those are the main portions of what we mean. So you've got a target material, energy to transform it, convert it to vapor, and then it condenses on your parts. And this all happens in a large vacuum chamber. So this schematic is a representative image of a typical VaporTech system. It's a large vacuum chamber vessel that is, we have the door open on this one so you can see what's going on inside. But this is a controlled environment at a low pressure, backed by a number of backing pumps. But inside, let's start at the center. So this very energetic looking device here, this is what we call our source or our cathode. This is a rod of material, or the target that I mentioned in the previous slide. This is our starting material. It can be really any metal. The only requirement is that it's electrically conductive. So we tend to use materials like zirconium or titanium. So we're starting with that material. We strike an arc on the surface, and that arc travels along the length and also around the circumference of that target. And where that arc is on the surface, it's actually vaporizing material and also ionizing material. It's ejecting material in 360 degrees around, and you have a very high energy of material coming off, a mixture of ions, which are energetic atoms that have had an electron removed, and that is getting deposited all around the inside of the chamber. Now, on the outside part of the chamber is where you put your parts or your substrates. They're mounted on racks that are mounted onto a carousel, and that carousel rotates around the chamber in one axis, and then each of those racks also rotates on an independent axis for second axis rotation. And this allows for good uniformity of coating coverage on parts as they travel around the circumference of the chamber. You know, one of the nice things about this configuration of having that target material in the center is that it's depositing material throughout the 360 degrees around the chamber. In some configurations, you have these sources mounted on the walls, which is then spraying material inwards towards the inside of the chamber, which is also a good way of doing it. We just prefer for most of our applications to spray from the inside out. It has a few advantages. Let's see what else we have in the chamber. We have our power supplies that power both the source, and we also have power supplies that drive a bias on the substrates. We apply a negative bias voltage on the parts, which helps drive the positively charged ions coming off of the target to it, which helps drive reactions and densify coatings. We're also introducing a number of gases into the chamber, and this is how we control the reactions and control the different colors, which we'll discuss in more detail later. So this is the configuration that we find in all the VaporTech systems. We have different sizes of chambers depending on the applications, the needs for throughput, et cetera. Okay, so I've mentioned Cathodic Arc. Cathodic Arc is the type of technology that we use in that center arc source in the chamber. Another type of PVD that's commonly used is called magnetron sputtering. I'm going to just do a little compare and contrast here just so you can get a little idea of the differences here, because they're both used and very commonly. So the biggest difference is energy. Cathodic arc is a very high energy process. Most of the material coming off the target is ionized. That's that positively charged aspect that I mentioned before. Magnetron, fairly low energy, small amount of ionization. There's ways to boost that with various configuration, but it's still fairly low. That energy helps us drive reactions at low temperatures, which is really key for a lot of the applications we work in, where we're trying to apply our coatings onto plastics or other temperature sensitive materials. Whereas in magnetron sputtering, sometimes to drive the same reactions, you have to use thermal energy. You have to heat parts up, which a lot of substrates can't accommodate. Another thing is target poisoning, which is essentially a surface effect that happens on your target, whereby it reacts with the surrounding gases like the oxygen or nitrogen. Cathodic arc is less sensitive. Magnetron sputtering is quite a bit more sensitive. So this is a lot easier to control the environment in which the coatings grow and react. The one drawback with cathodic arc is the amount of defects that are ejected from the process. Now, these are really small liquid droplets that occur because it's such a high energy process. The nice thing about decorative coatings is they're so thin that these macro particles really don't play a role. They're invisible. They don't have any real effects. But in contrast, magnetron sputtering has many fewer. It's not a no defect, but it has much fewer defects than from cathodic arc. So due to these reasons on the left-hand side, cathodic arc is the preferred method for most of the decorative coatings that we use, but they can also be used in conjunction. Very often, using them together, whether or not making multi-layer coatings, or magnetron sputtering is also used for some of the CVD coatings that we're going to talk about later, some of the diamond-like carbon coatings. Okay, so let's switch gears and talk about the coatings themselves. So when I mentioned earlier, I talked about the natural coatings, the coatings in which that we are trying to mimic those natural alloys, such as the coppers and brasses and such. So these coatings tend to be opaque, meaning that they don't transmit light through them. So what you're seeing is the colors that you're seeing are defined by the reflected light of what's coming back to your eyes when you see this. And the nice thing about this is that that color is defined by the material properties, the compound that you're making, the material itself, and it doesn't change with thickness. So as you're building a thicker coating, the color doesn't change. You can be very thin coating and get the same color. You can be as thin as 1/10 of a micron or 100 nanometers, but more often than not, our coatings for decorative tend to be in the 1/4 to 1/2 a micron range, as opposed to, say, thick functional coatings for wear applications, which could be many times this thickness. Because these coatings are opaque, it really works well for complex geometries. If you have parts with a lot of different features and you want to get a uniform color all over it, you really want to work with an opaque coating. And again, like I mentioned, these coatings are generally mimicking the look of pure metals and alloys. For example, we can match the color of things like gold. We may not be able to make them look exactly like gold, but it's a good representation, and generally, unless you're comparing them side by side, you're not really going to notice a difference. Some metals we can match almost exactly, stainless steels, nickels, brasses, for example, but some of the materials like coppers and golds are really, really difficult to get an exact match. And a lot of that has to do with the electronic structure and the conductivity of those materials that you just can't match with any other materials. And really, these are the majority of our decorative coatings. The other type, when I was talking before, I mentioned artificial coatings, which may not be the most natural of looking ones. These tend to be made by optical approaches, where these coatings can be transparent or they can be semi-transparent, meaning that the color is often driven by the thickness. If it is below a critical thickness, it can be, you can get some interference colors, some rainbows, or some of these vivid colors like these blues, vivid blues, come from an interference effect. But once you get above a certain thickness where all of the light is getting absorbed by the coating and no more is getting reflected from the undersurface, it will then become opaque. But it takes a much thicker layer before it becomes opaque, sometimes as often as a micron thick. And this is common for things like metal oxides and diamond-like carbons, DLCs. And those are good examples of those. So let's talk a little bit about the starting materials we use. What are we using to make these coatings? So when we talk about the metals or the substrates, we have 3 main metals that we work with. It's not exclusive to these. Like I said, any metal can be used, but in order to form the types of coatings that are most commonly used, we use these big 3: zirconium, titanium, and chromium. And by far, zirconium is the most popular, and we'll talk more about that. And then reactive gases. We use very common industrial gases: nitrogen, oxygen, methane, acetylene. These are very common, inexpensive gases, easy to acquire. And between these 7, just these 7 ingredients, almost every single coating we talk about can be made. So speaking of these materials and these reactions I've mentioned, what class of materials are we talking about? So we're talking about nitrides, carbonitrides, oxycarbides, all sorts of different compounds. And so the properties they have and how we describe them, often they have very ceramic-like properties, but traditionally ceramics are hard and brittle and insulating. These materials generally are hard and brittle, but they're also very conductive. So they're more like ceramic, like cermets, which is kind of a hybrid between metal and ceramic. Hardness can be as high as 10 times as hard as a base metal. Good example is titanium. Titanium metal itself, very soft. Titanium nitride, extremely hard. And like I said, most of these do remain electrically conductive, which allows them to retain their reflectivity and their shiny nature to mimic metals. And typically, these types of compounds are going to be more chemically inert than the base metal they started with. You know, a titanium oxide, titanium nitride is going to be more inert than a titanium metal, for example. Okay, so let's talk about each of these individually. So let's talk about zirconium first. Like I said, this is the one that we use most often, by far more than any other. 14 of the standard VaporTech finishes are based on this. I think we have on the order of 20 or 22 standard ones. So 2/3 of them are based on zirconium. And this material, not only can you make a lot of colors, it also has the best chemical and corrosion resistance. It's just a really durable metal. It's very stable in a wide range of environments and against various chemicals. So the types of coatings, again, these kind of compounds we talked about before, the nitrides, carbonitrides, wide range of different colors, anything from the brasses and nickels to you start adding some carbon, you start getting some of the redder yellow metals, some of the golds, bronzes. We're going to talk a little more about our Oxycarbides, which is a unique coating family where we get some of our blacks and graphites, and then zirconium oxides, where we get some things like some stainless steels and blues. So just an example of how we can use the same compound but get wildly different colors. So let's talk about zirconium nitride, widely used to make colors such as nickel and brass. So this is a little bit simplistic, but basically if you have a low amount of nitrogen that you're introducing into your chamber, you can form more of just a pale yellow nickel color. However, if you add a lot of nitrogen and you fully react your zirconium with nitrogen, it looks just like brass. And this the 0.2 here just basically indicates that you don't have it fully reacted. This is where you have perhaps a solid solution of nitrogen in with the zirconium. It's still going to be much harder than pure zirconium. However, because it's not fully reacted, it doesn't have as much of the ceramic-like qualities, and it's not going to be quite as hard as something that's fully reacted, like a brass-colored zirconium nitride. Still going to have a lot of great properties, but just a little different. And we can change between these colors, and you can get anything in between just by modulating the amount of nitrogen that you're introducing in the chamber. And very similarly, nitrogen and carbon gases, you get carbonitrides. And there are two carbon gases we use most often, methane and acetylene. They can often be used interchangeably, but just in this quick example, sometimes you just get different shades of colors. And we tend to get a little bit more red when we start using acetylene than we do with methane. So you get some more of the rose gold colors. However, with methane tends to be what we call a cleaner gas or more thermally stable. So it tends to be a bit of an easier process to control. However, acetylene can give us a little bit of a different color palette as needed. And this is one, zirconium oxycarbides, or like what we like to call them, ZrOC. That's our internal name for it. This is a family of materials that we patented quite a while ago. But so this is a unique family of materials at VaporTech, and we can get a wide variety of different colors with this material. So these are in the range of those optical coatings that we were talking about, and we can get a variety of shades just by modulating the amount of oxygen and carbon in these gases, anything from a kind of a dark gray that we call graphite, or we can even go into what we call a true black, which is a very dark neutral black color. And then within each of these graphite and true blacks, we have ways in which we can modulate it to the blue side of things and make things that we call cool, which is maybe has a little bit of a blue tint, make a blue black, for example. Or we can go in the other direction and go into more warm colors where there might be more of a yellowish or red tones, where we get kind of warm graphite. So we've got a wide range of different types of colors that we can achieve just with this one material. Switching gears to titanium. This one's like I believe I mentioned earlier, the longest history of use as a decorative coating. This is where some of the original work was done back in the 80s. You're probably very familiar with the work that it's done in functional coatings on tool coatings and such. Very similar as zirconium as far as the types of reactions that occur. Tends not to have as wide of a color palette, so it doesn't get used as often, and it's not quite as stable with chemicals or corrosion. But you can get a lot of the golds and rose golds and bronzes with titanium as well. And then there's chromium. Chromium, generally shades of gray and silver. It doesn't have any of the yellows and reds that you get with the titaniums and the zirconiums. However, you can get some really nice colors that are very attractive. Chrome is very commonly used in electroplating. We have a way in which we can mimic that same finish with a PVD, clean PVD process. You get silver or aluminum type colors, stainless steels, going into the dark grays and blacks. And then I do want to mention a little bit about diamond like carbon, DLCs. This has really been growing over the last few years, a high demand for use as a decorative coating. And this is an example of what it generally looks like. We see it quite often in sporting goods with golf clubs. It's a very durable coating. It's got one of the characteristics of it. It's got very low friction, which means that, even though it might not be as hard as some of the other coatings, just because it's got low friction, it really helps hold up against a lot of abrasive wear. Not a lot of different colors you can get, really just dark grays into maybe some of the black colors. Some limitations is that it is a thicker coating because it's an optical coating. You have to be above a certain thickness before it becomes opaque, and also requires some higher temperature processing. So you don't really see this one applied on plastics and such. It's really limited to metallic substrates. There are a few ways to do this, one of which we have not talked about yet, which is plasma enhanced chemical vapor deposition, or sometimes plasma assisted chemical vapor deposition, or PECVD, which is a method in which we use acetylene gas or methane gas, break it down with a plasma and form a coating based on that. Or you can also use sputtering, starting with a metal material, very commonly tungsten. You could also use chromium, where you're sputtering metals like tungsten in an acetylene environment, and you can form these tungsten DLCs. They go by a lot of different names, WDLC, WCC. They're generally the same thing, but just different nomenclatures you might come across. Okay, so I know we have only got a few more minutes here, but this is a topic that's really quite important as we talk about decorative coatings. And I think we could probably have an entire webinar on this topic by itself. But I just want to go over some of the high level aspects of it that are important takeaways, I think, for this audience. First of all, color is something that we can actually measure. Of course, it's very subjective. It's something that, we look at something with our eyes, but of course, in the engineering world, in scientific world, we like to be able to put a number to things. We like to measure it. And we measure things by use of a spectrophotometer, which is an instrument that essentially shines a light on an object and then looks back at the light reflecting back, and it identifies a coordinate of color that lands within this 3D spherical representation of all the colors available. So this is also called the C-Lab color space model. Let me just walk you through how this is laid out. So the L is typically the y-axis, which is the white to black. So something that is fully white would have a L of 100%, and something that is completely black and non-reflective would be a 0. And then as you're looking at the color hues, you have the A component, which is the red and green axis. So as you start with a negative A, you are on the green spectrum, and then as you move to a positive A, you get into the reds. And very much the same way with the B, which is the yellow-blue axis. As you are at a negative B, you are in the blue. And then as you move towards the positive B, you are into the yellow. Another concept that you will often see if you're talking with people about color space and color numbers is a delta E value. And this delta E value is essentially when you're comparing two colors, how far apart are they within this color space? And this is often used when you have a target color, or what you're trying to achieve, and then what you actually get. So if you have from your quality control for a certain color, you're shooting for a certain color, and you always want to know, well, how far away am I? And you just use this nice equation, which is basically just the distance in a 3D space between parts. So you just take the difference of each of the components from your target, square it, and then you sum it up, and then you take the square root, and you get a number. And the larger that number is, the further apart they are in that space. And that's a way you can gauge how far away from your target you are. And just as an example, if you've never seen a spectrophotometer before, this is just a handheld model in this picture. Different versions of it. Most of what we use are handheld. They're also benchtop models, but this is just one that works. And let's say we're taking a picture of this yellow piece. It's going to spit out a number. For example, it's got a high value of L, which means it's fairly reflective and bright. It's got a little bit of red in it, which means it's got a value. And of course, it's very yellow, so it's got a very high B value. And of course, that'll land somewhere in this spectrum here. So just an idea of how that works. So color measurement, one of the things we always like to warn people about is it's very valid on flat surfaces, but we always caution people in trying to use it on complex geometries. Due to curvature of surfaces, it can also often throw off the values or introduce more noise. And also surface texture. If you've got a brush texture or something like that, it can also throw off your measured values. And so you have to be really cautious about that. For production control, we often recommend that our customers implement using witness coupons. And what do I mean by that? They're basically just little pieces of metal, usually stainless steel, that you'll include in each of your runs. It's a controlled surface that's always the same every time. Put that in the chamber along with the parts you're coating. When you take it out, you shoot the number, and then you can plot it on a statistical process control chart, which is just a really nice way of being able to monitor the performance of your system and making sure that everything is in control. It's a little bit harder to do with visual assessment because that is very subjective. However, we always like to use data to drive our processes and control them. And one last thing I'd like to talk on my last couple minutes here is just about color judgment, in particular visual assessment. Now, we've been talking about instrumentation, very important. However, at the end of the day, it's really how it looks to our eyes. And ultimately, passing and failing components that have decorative coatings generally falls in on, at some point you have to do some visual assessment. And often our customers will use visual standards, meaning it's either a range of sample parts or sample coupons that are representing the highest range at which it's acceptable for color variation. So often a light sample and a dark sample, you would take a part out of the chamber, look at it, and see whether or not it falls between those standards. Again, it's really important the environment at which you do these judgments. We tend to use light boxes, recommend light boxes, which are controlled areas where there's controlled light, neutral colors within. So you can, whether or not you want to have daylight or fluorescent lighting, you can control the light because that has a big influence on how you perceive the color of a surface. And then another thing is you really want to make sure if people are doing this visually, that your inspectors are qualified. A big issue is color blindness. 1 out of every 12 men have some degree of color blindness, 1 out of every 200 for women. One of the ways in which this is evaluated is this Ishihara test, which is, you've probably seen these before, but a collection of colored dots, and you're looking to see if you can distinguish the number within. There's standardized books on this, but I found there's also free apps for your phone that you could just download and do a quick test. It's probably not the best official test, but if you want to get an idea of whether or not you've got a deficiency or your inspectors have a deficiency, it's probably a good first pass. Very similar to color blindness is the ability to distinguish between hues. And this is the Farnsworth-Munsell test that we also recommend. And this is just a series of little pellets that have varying shades of color on them. And the idea is you start these out mixed up and you are to put them in order of graduations of color. So if you can put them back in order, in the right order, that means that you are good at being able to distinguish very fine changes in color hue. So both very, very useful tests to assess your inspectors. One last thing I want to say, and it's been a very important learning over my 20 years of working in decorative coatings, is how important the influence of surface texture has on color mismatch and judgment. I can't stress this enough. And one thing we haven't really talked about is that these coatings are so thin, they can be applied on any kind of textures, whether it's brushed or a matte texture. and we don't really change they're thin enough that they don't really change the texture. However, those textures can have a huge impact on the way you perceive color. For example, if you were to put the same parts in the chamber, apply the same color on something that's highly polished versus something that's got a matte surface, the polished surface is going to look much darker than that has a matte or a diffuse surface. And that has to do with the diffusion of light and what's getting reflected back to your eyes. And it can be very tricky if you're trying to judge parts that you may have different texture, if you've got different suppliers, vendors providing too much variety in texture that can really throw off your color. So just a word of kind of a pro tip from here. Just be very cautious of that when you're judging color.